This is proton NMR, and nearly all the hydrogen atoms have an isotope like this, rather than this one or that one. So most of them are that one. So it's nearly 100%. And what that means, unlike carbon-13 NMR, is that it's much easier to get a spectra. So we actually need a slightly less sample to get a proton NMR. And here it's the hydrogen atoms which are attached to different functional groups, feel the magnetic field differently, so you get different hydrogen environments. So let's have a look at our data sheet again. So we've got our infrared, carbon-13 NMR that we've looked at, and then proton NMR. We notice here this time our chemical shift values only go up to about 12 rather than over 200. So the chemical shift is a lot less. And we can see in this case that our hydrogens are in bold here. So we've got here an alcohol hydrogen, CH3, an amine, CH2, CH, a hydrogen adjacent to a carbonyl. Now adjacent means that the hydrogen is not attached directly to that carbon of that carbonyl, so it's adjacent to a carbonyl. We've got a hydrogen which is attached to a carbon which has a single bond oxygen. We've got a hydrogen next to a chlorine, bromine or iodine, so we find those CH2 hydrogens next to the halides in a haloalkane. We've got a hydrogen there which is attached to a carbon, which is attached to an oxygen, which is attached to a carbonyl here. So we find these in esters. We've got an alkene hydrogen and a carbonyl hydrogen. Notice this one here is different to that one there. And at the bottom here we've got an OH again, but you can see that that OH value there is completely different to that one there. So that's the alcohol and that's the carboxylic acid. So again, just like I suggested with the carbon-13 NMR, I would suggest that you print a copy of this data sheet off and write those notes down on your table B. So you might want to rewind the video now to do that. So we're going to need this during this video. So let's have a look at our carbon environments and our hydrogen environments. So a very simple molecule here. If this was a carbon-13 NMR spectra, it would have one peak. Now, if we have a proton NMR, it still only has one peak. And that's because all of these hydrogens here are in the same environment. They're what you call equivalent. Equivalent means in the same environment. But in a molecule like methanol, which is like this, there are hydrogen atoms in two different environments. There's the 3 on the carbon atom, that's one environment, and the 1 on the oxygen atom, that's the second environment. And the carbon-13 spectra will show the two environments. So 0, one of our standard, TMS, and let's say at around 3.4, my peaks are slightly different this time. It looks slightly different to a carbon-13 NMR. I've exaggerated this a little bit. I'll come back to that in a second. So I have a peak there at around about 3.4 and another peak here, slightly smaller one at 4. Now, in general, the further away the hydrogen atom is from an electronegative atom, such as an oxygen, the smaller the chemical shift. Okay, so in this molecule here, we have 2 different hydrogen environments. So this particular peak here is quite close to the oxygen. So that hydrogen there corresponds to this peak. And this hydrogen environment here corresponds to this peak. So in general, the further away a hydrogen atom is from an electronegative atom, the smaller the chemical shift. So these hydrogen atoms are quite far away from this oxygen, so they have a small chemical shift. And this hydrogen atom here is directly bonded to the oxygen, so there's quite a big difference between, compared to this environment here, between that and the chemical shift of that one. So just a quick way of analysing them. But really, we should be looking at our table of data, table B on our data sheet. So, what have we got? We've got an alcohol hydrogen, which is this one here. So from 0.5 to 5. That isn't from 0.5 to 5, that's within that bracket, so that is an alcohol hydrogen. Then here we've got a CH3, so it's a CH3. Now notice that R group there can be anything. So these can be anything. Now in this case, that R group there is actually an OH, but we're not really interested in that. We're just interested in those hydrogens that I'm talking about, the bold ones. So this is a CH3. So whenever you see a CH3, it's somewhere between 0.7 and 1.2. Okay. Actually, so that would be a little bit out, actually. Beg your pardon. But we get the idea. Now, let's have a look at the size of these peaks. We can actually calculate the area underneath these. Now, we can then look at the ratio between the area of that peak and the area of that peak. Now, if this is a 1 to 3 ratio, we can tell that there are 3 times as many hydrogens that are corresponding to this peak compared to that one there. That's another way of working out that that peak there corresponds to this one, and this peak here corresponds to these 3 hydrogens here. Now, sometimes though it's quite difficult to see. So, an instrument produces a line called the integration trace. Now, an integration trace sometimes looks a little bit like this, over the top of the peaks, like that. Okay, and that just gives the length of this area here, and the distance here. That distance there is 3 times the distance there, so it gives it a better indication of the area underneath the peaks. And we'll call that the integration ratio that's produced. So these 2 peaks here have an integration ratio of 1 to 3. Now that doesn't necessarily mean there's 1 hydrogen in one environment and 3 hydrogens in the other. It could mean that there's 2 hydrogens in one environment and 6 hydrogens in the other. Or, let's say, 4 hydrogens in one environment and 4 times 3 is 12 hydrogens in the other environment. So just be careful about that. So let's have a look at our tetramethylsilane now. So why is it that we use TMS, tetramethylsilane, as our solvent? So let's just recap that all the chemical shift values are measured with a reference to this standard, and it's the chemical shift of the hydrogen atoms in this compound, TMS, that is used as our standard. Now this is the structure of TMS. Now I would suggest that you learn this. Let's look at the name, tetramethylsilane. Should just be an E on the end there. So tetramethyl means 4 methyl groups attached to a silicon. So how many hydrogens have we got here? We've got 12 hydrogen atoms, which are all in exactly the same environment. There's no way of telling the difference between all 12 hydrogens. Because we've got 12 hydrogens in there, for every one molecule, we'll only need a small amount of this in our sample. Because we've got 12 hydrogens per molecule, so a few molecules will produce quite an intense peak. And this TMS here is a liquid at room temperature, which you add to the sample before you run the NMR spectra, and it gives a peak at 0 parts per million, and you calibrate the computer which is producing the spectra to 0, and then everything is compared to that. So some reasons why you use TMS. It's inert. Obviously we don't want that to start reacting with our sample. It's non-toxic. We don't want to poison the person who's carrying out this technique. And it's easy to remove from the sample. If we want the sample back at the end, what we can do is we can evaporate off the TMS, leaving the original sample. And the fourth reason, just to recap of this, you only need a small amount. And this is due to the intense peak that it produces. And of course, it only produces one peak. And it's actually the same solvent, the same standard rather, that is used in carbon NMR as well, because we can see here that there is one carbon environment as well. Here, and there's 4 carbons. So it's the same solvent that we use. Nowadays, though, we can actually get away with not actually using a standard like this.